Ayan. Okay. Okay. Sige, let's continue. Ah, so numerical methods is used by the computers to solve um, to solve to perform calculations. Of course, hindi naman natin kayang i-instruct yung computers because computers can only understand the binary language. So we find a way to utilize that in order for them to solve some complex mathematical problems. Ayan. Sige, let's continue. On the other hand, what we do in real life, what we do as humans is called the analytical methods. Okay, so these methods are derived from logical thinking and logical thinking or from mathematical axioms that you learn, of course, from your mathematical math courses. Ayan. Sige. And the solution for analytical methods are called the exact solution. So sila talaga yung exact. Doon sa numerical methods, sila yung approximate solutions. So just take note of that. Especially, different computers have different accuracies, no? So just take note of it. Yeah, basically everything 21, 22, 23, CE 24. Okay. So specific implementation, termination criteria. Basically just a definition of an algorithm. Ayan. A numerical method is called convergent if the corresponding sequence converges to a certain value for a given initial approximation. Like what I showed you earlier, yung sa calculator example ko, right? Sige, pakita ko ulit. Like in this example, we call the first example as convergent. Ibig sabihin, nag-converge siya sa isang value. Okay? But uh, but our numerical methods can also be divergent. Ibig sabihin, kahit anong gawin ng numerical solution ko, ng numerical method ko, I cannot get a solution. In this case, no solution nakalagay, ibig sabihin, divergent yung method na ginamit ko. Hindi siya nagko-converge sa isang value, divergent. Okay. Ayan. Let's continue. To be useful, an algorithm should be stable. That is, small changes in the initial data should cause only small changes in the final results. So when you say stable, you will see this in the later modules, but sometimes our solution jumps yung results niya jumps from one value to a higher value drastically. So in that case, yung algorithm nyo is not stable. This are just definitions, but I hope you can see this in the next modules. You will see this in the next modules. Ano yung mga ibig sabihin ng pag ganito, no? Okay. Since approximate solutions lang yung solution na binibigay ng numerical methods, of course there will be errors. Okay? So just take note of it. Yeah, so we have round off errors and truncating errors. This one is ano eh, um, I can cite a story from the book, a book that I've read from earlier this last year. It discusses chaos theory. So there was and chaos theory began began in weather reporting or weather predictions. Okay? So yung isang scientist, I forgot the name. May isang scientist na ano eh, na nagre-record siya ng weather every day or at some interval of time. I don't know, every minute, every hour, and then recorded it to some instrument from an instrument. And then what he tried to do is to predict the weather. So doon nagsimula yung weather prediction. Now for a certain amount of time, accurate yung results niya, no? So nagpo-produce ng accurate weather for a certain day. Nape-predict na yung weather. But as time goes by, habang lumalayo siya ng lumalayo doon sa day kung saan meron siyang data, nagiging lumalaki yung error niya. And what's happening there? What's happening there is that yung instrument niya, it can only measure so much accuracy, no? Hindi masyadong accurate yung instrument niya that it rounds off data. Okay? It rounds off data. And it turns out that that round off, even though it's very, very, very small, it's very, very, very small, malaki yung effect niya dun sa error. Okay? And that's what they call a data that is very sensitive to the initial conditions. Okay? So, very sensitive yung data niya to initial conditions that even some round of errors, hindi siya makapag-round off ng maayos. Kaya there are problems in science and engineering that still has a very chaotic data because of this, no? Pag yung instruments natin, it can only acquire so much accuracy. So that's one thing. Also, of course, kasi yung instruments natin includes also computers, no? So, ayun, your computers can only have so much accuracy. Ayan. So, very common ang numerical methods sa round of errors. Truncating errors, this is basically on how you derive your numerical methods. As you can see earlier, what this truncating error means, but you can actually measure this, no, from your assumptions on the numerical methods. We will explore this later. Ayan, so this is just the definition of error. So absolute error, xe minus xa. So this is the exact, okay, exact value minus the approximate value and take the absolute value. That's the absolute error. And we also have the relative error. Okay? xe minus xa over xe. So I think nadaanan nyo na rin to sa physics nyo kung naglalab kayo. So you have this sort of experimental error minus theoretical error, di ba? Pero here, since we already know we know the exact error, sometimes we know the exact value, but most of the time we have we only get the approximate value. So, ayan. Ito yung mga measures ng errors natin. Again, this is the general steps of numerical methods. So it starts with an initial guess, and then it performs the numerical method that we will discuss later, and then repeat. Yan. Iterate until it arrives to a termination criteria, and wherein the iteration or the repeating of the algorithm stops. In that case, it will tell you if the value converge or the value diverges to a certain answer or solution. Okay, not all occasions can be applied to some numerical methods. So just take note of the assumptions that we will discuss later. The assumptions that limits, of course, limits the power of the numerical method. And the rules depends on the initial guess. That happens most of the time. Okay? Kapag guess nga no, kapag malapit yung hula nyo doon sa tamang sagot, mas mabilis mag-converge yung numerical method nyo. Okay? Kapag masyadong malayo, then it might diverge or it might get some wrong solution. Okay? Sige, termination criteria. Sige, iteration should terminate if either of the following condition is satisfied. Ayan. So meron tayong tinatawag na tolerance, no? Tolerance. In this case, okay kayo na may ganong error yung numerical method nyo. Siyempre in engineering, as I've told you at some point in class, I think I've told you na hindi naman kailangan na masyadong accurate yung or masyadong hindi naman kailangan masyadong accurate yung solutions nyo. Again, it depends on your measuring devices. If hanggang 2 decimal places lang yung kaya ng measuring devices nyo, then your tolerance should be at that degree. No? So, ganun natin determine yung tolerance natin. Or, you have reached the maximum iteration. Siyempre, hindi nyo naman ma-afford, no? Na hanap ng solution yung numerical methods niyo forever, no? So we tend to have some specified maximum number of iterations just for us to gauge if divergent ba yung solution ko. This number is actually from experience na siguro na makita natin kung gaano ba kabilis yung computer niya, how much you want to spend time in finding a solution. Sige. Any questions so far in that? I think hindi pa masyadong ma-appreciate, no, ngayon. Just discussing those abstract things. But I guess when we discuss more of the methods, then you will appreciate it. Okay pa? Yan. Please click yes kung okay pa. Okay, sige. Yan. Now we start with numerical differentiation. What is numerical differentiation? Basically, you get the derivative. Okay. Yan, dapat experts na kayo dyan, no? Numerical differentiation is the computation of values of the derivative of a function f from a given values of f. Okay. Why differentiate numerically? In my experience, pag meron akong numerical project na ginagawa, I don't usually do analytical differentiation. I go direct to differentiating numerically. Why? Because it's easier. It's easier. Yan. So, also, tingnan natin yung bullet 1. Yan. Sampled data set without the function, knowing the function itself. So, sometimes, in a lot of things in the real world, you don't know the function. For example, do you know yung sinabi ko sa inyo kanina? Weather at this point, or the chance of rain, for example, so weather. It's a very complex thing to model that hindi natin kayang mag-fit ng equation for a lot of variables, di ba? Yung weather siguro a function of the weather from the previous from the previous recorded day, or the temperature, something like that. It depends on a lot of variables. So hindi natin kaya. Ano pa? Um, even in simple things. So kunwari, uh, how much energy you have in class, for example. Siguro it depends on your on the food you ate, the motivation you have. But in this case, it cannot be modeled in one function or in one equation. So ang ginagawa natin, we survey things and get the data, and then from the data, we 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 approximate. Yeah, we approximate the derivative if you want to get the derivative. Okay, without even knowing the function itself. So that's one case. Or exact computation of derivative may require a lot of function. This is what I'm saying. It's very hard to get the derivative of one function sometimes. Yeah. So again, I resort to numerical differentiation. Ayan, sabi dito, numerical differentiation should be avoided whenever possible. If you have the exact function, and if you can differentiate the function, then do theoretical or do the analytical method. But again, in real world problems, this is not usually the case. Ayan. Numerical differentiation, a simple approximation of the first derivative can be given as this. So where this does come from? This is the very definition of derivative, di ba? This is the very definition of derivative. Ano lang dapat yung derivative natin, meron lang siyang ganito eh. Meron siyang meron siyang limit tama, as h approaches 0. Yan. Yan yung mathematical definition ng derivative. But we can approximate the derivative of a function at a point by just saying that hindi na lang 0 yung h ko. I will just say that h will be very, very, very small. So by substituting a very, very, very small h, I can get an approximate solution or approximate first derivative. Okay ba tayo? So ayan. This one is what I'm saying. This approximation comes from the definition of the derivative limit as h equals 0. Yeah. So what I should do is that I should just substitute instead of 0. I will just substitute h to be very, very, very small and then compute it. Ganun lang siya. However, for almost all functions, the equation given does not give the exact derivative. Okay. For example, in this case, approximate the derivative of the function at x equals 1 using different values of h. Okay. So, ayan. F of x equals e to the x. Now, we know, anong derivative ng e to the x? Ano yung exact? Tama, no? E to the x. Yan. Very good. So, ayan. Now, we approximate using the definition in the previous slide. We just substitute 1. So, f of x plus h is this. And then f of x is this. Then f of x Okay? Plus h minus f of x is this. Therefore, okay, therefore, the f of prime is this. Is this correct? Dapat nakalagay dito yung error. No? Dapat ang sagot is 2.7, di ba? 2.7. Ayan. So as we decrease the value of h, okay, what happens? It approaches 2.718. But here's the catch. Ano nangyari dito? What happened here? Do you think? Nawala yung screen ko. Yeah. What do you think happened here? So, let's see. Problem with h. Okay, when h is large, the difference quotient is the slope of the secant line joining 2 points that are not close enough for to each other. Okay, so magkakaroon ng malaking deviation from f prime of x, from the actual value of f prime of x. But when h is too small, ayan, the difference quotient can exhibit the problem of loss of significance due to the subtraction of quantities that are nearly equal. Ayan. So, nagkaroon tayo ng 0, 0, 0 dito. This one depends how small, okay? How small your data is, how small the results here, is dependent on how accurate your computer is. So ito yung sinasabi ko sa inyo na accuracy ng computer nyo. Okay, so the computer can only do calculation at this number of decimal points. So kung masyado nang maliit yung difference nila, hindi na niya mare-record, no? So ang ilalagay niya lang dito 0. Okay, so it results to a wrong answer for f prime. So balancing out lang kung ano talaga yung small. No? Okay. Next. Yeah. So since the results are not exact, approximation errors exist. And this is what this is where we discuss truncation errors. So natatandaan niyo pa yung Taylor series? From anong math ba 'yon? Math 22. Iba na kasi yung title ng math ngayon eh. But this, I think this is discussed in math. Okay. Okay, sige, okay lang 'yan. We'll review Taylor's series. We'll review Taylor series. So this is the Taylor series. Okay. Ayan. So f of x plus h can be approximated and by this series. Okay. So f of x plus h, where h is this one. H f prime of x, h squared over 2 f double prime of x. Yan. Actually, tuloy-tuloy pa to eh. H over 3, h cube over 3 f 3 of x. Okay, hanggang sa dulo. Now, rearranging this equation, okay? Rearranging this equation and solving for f prime of x, we get this. Okay? And this is what we call, let me just encircle. This is what we call, this is what we call the truncation error. Okay? That's what we call the truncation error. That is an inherent error of the method. No? So whatever you do, it will, the result of your analysis will never be, okay, exact. Okay? So yan yung tinatawag na truncation error from the previous slide, yung define. Now, yan. Ito lang yung numerical differentiation approximation na ginamit natin. So, yan lang yung, hanggang dyan lang yung kaya natin i-approximate. This value, hindi na kino-consider ng numerical method natin. Now, you might ask, are there other methods on how to improve this method? Diba? Para mas, siguro gusto nating paliitin to lalo, no? Ayaw natin ng truncation error na wala na tayong magagawa. Actually, there is, okay? So, and then, let's explore more methods. Yan, truncation error. Pth order method. Yan, the accuracy of the method is reflected in the order O of the truncation error. So what does that say? So from this approximation from the last slides, this one is of order 1. Now it has an order of OH and thus a first order method. So ayan, hanggang dito lang tayo umabot. H is of order H. Yan yung error, yan yung order ng error, ng truncation error natin. Okay? Sige, let's move. An approximation of the derivative at x based on the values of the function at x and x plus h. This is what, yung method natin na ginawa from last slides is called the forward difference quotient. Why is it called forward? Because it uses plus h, okay? X and x plus h. So this is called forward. Okay? Yan. Uses x plus h. You'll see later, of course, meron tayong tinatawag na backward difference quotient. Sige, let's see. Yan, backward difference quotient. In this case, instead of using x plus h, we use x minus h. So that is called backward. We stepped backward. Okay? So yun lang yung pinagkaiba. Next, meron din tayong tinatawag na central difference quotient. Okay? So paano ba yan? The central difference quotient, we don't use the x, rather, we use x plus h and x minus h. Ano kaya yung mas accurate sa tatlo? Could you guess? Could you guess? Sige. Ayan. Has higher accuracy than the first two. Bakit kaya? Yan. Because it has of order h squared. So this again is from the Taylor series. Probably, para mas ma-appreciate nyo. Is it showed here? Oh, may order H4 pa. Sige, probably, I'll show you how to derive this. Yan. Para naman confident kayo. Okay? Let me just stop share. And so, again, we define the Taylor series. F of x is equal to wait lang ha. F of x plus h is equal to f of x plus h f prime of x plus h squared over 2 prime f double prime of x plus h cube over 3 prime f triple prime of x plus so on. Okay, so this is the Taylor series. So how do we go to the central difference method? Okay, so we solve for f prime of x. So solving for f prime of x. F prime of x is equal to f sandali lang. Sorry. I remembered na. Now, we also have to define, ito yung magic ng central difference, x minus h. So this one is f of x minus h f prime of x plus h squared over 2 prime f double prime of x plus minus na pala. Minus h cubed over 3 prime f triple prime of x. Okay. Naintindihan so far ito? May tanong dito? Bakit ito minus? Kasi minus yun. Bakit ito plus? Kasi bakit ito minus? Kasi minus to. Bakit ito plus? Kasi negative h squared is h squared. So, magiging positive siya. Ito, negative, negative, negative. So, negative. Okay? Now, the magic that I will do is I will do this. F of x plus h plus f of x. Minus pala. Sorry. Minus f of x minus h. So this one is equal to, so nawala itong f of x, no? Minus, so magiging 2h f prime of x Ito, pag minus, so mawawala. Ito, so plus 2h cubed over 3 f triple prime of x plus, okay, probably, sige, para hindi tayo malito. May discussion kasi ako na uh, connected to this eh. Isali muna natin yung h squared. 2f of x, okay, plus 0 yan, no? 0. Plus 2h cubed over 3 prime f triple prime of x. Plus, and so on. So what happened here? Solving for f prime of x, okay? Solving for f prime of x. Delete na natin to para may space tayo. So this one, delete. Solving for f prime of x, what we have is f prime of x is equal to fx plus h minus fx minus h divided by 2h, okay, minus 0 h squared over 2 prime f double prime of x minus 2 h cubed over 3 prime f triple prime of x, and so on. Okay? Minus pala. And I will just say that f prime of x is equal to and x minus h over 2h minus a truncation error of order h squared. So that's what I will say. So this is the formulation of the central difference method. And as you can see, I have an error of order. So ang pinakamalaking order ko is h squared. Okay? So even though nag-cancel naman yung h squared, pero the order pa rin is yung highest value, even though 0 yung coefficient niya. Okay? So ganun yung convention natin na i-add up. Okay? So I guess we can go back to our slide. Ayan. So this is the truncation error as you can see earlier, as you saw earlier. And for order h, I'll leave it to you to try to derive this from the Taylor series. But basically, it's just the same thing. It's just the same process. Okay? Yeah. So lahat ng difference methods natin, ng numerical differentiation methods natin, is derived from the Taylor series. Ayan. Let's have an example. So, example 1b, f of x equals cosine x. Calculate approximations for f prime 0.8 using the two central difference approximations with step sizes 0.1, 0.01, and compare with true value of f prime of 0.8. Okay. So here, let f of x equals cosine x. So these are the formulas, no? Formulas for central difference. So this is the second order and this is the fourth order. Okay? Now, this one is the h. Okay? So second order approximation. Now, substituting here, we get these values. Note lang ha, kung itatry nyo ito, okay, note na yung x is in radians, no? Hindi in degrees. That is in radians. So just take note of it. Ganun yung convention natin if nasa math tayo. Okay? And the error is this. As you can see, as you decrease, okay, the value of h, of course, the approximation is more accurate. And for fourth order approximation, ayan. Again, as you decrease h, it becomes more accurate. What else happens? As long as you increase the order of approximation, the truncation error decreases. So, ayan, mas accurate ito, itong side na to, yung fourth order approximation, kaysa sa second order approximation. Okay. Right point. Now, pwede niyong tanungin, sir, kailan ko gagamitin yung second order approximation, fourth order approximation? Kailan ko gagamitin yung central difference over forward difference? It depends on you. Also, it depends on your computer. For things that are very easy to differentiate, if kaya ng computer nyo na mag-iterate so many times just to get into the if kaya ng computer nyo na mag-approximate up to a certain point, okay? Up to this accuracy of h, then I think second order approximation would be enough. Okay? Ayan. So kung tingin nyo, hindi nyo naman kailangan ng fourth order approximation, then it depends on the problem. Okay? And it depends on you. And the machine that you have. Differentiation via interpolation. An approximation of the derivative at any point in a set of ordered pairs can be obtained by direct differentiation of the interpolating polynomial. Ayan. So this one is for okay, this one is for data sets, no? For data sets where you don't have a defined function. Okay? A defined function. So this one is what you will use. Basically, this is just like interpolation. But anyway, we'll not use this in this class most of the time. Okay. We'll not yet use this in this class. Okay. So this is the derivative approximation. This is the truncation error. Again, this is a good to know thing, but if you want to explore more of this, then you may do so. Medyo nagkagulo ng topic, no? That's why I'm not discussing this yet. Kasi we haven't discussed yet Lagrange interpolation. Okay? We will discuss this in the next modules. So hindi namin to na-consider. Sorry. Anyway, we'll just skip that and siguro we can go back to this when we discuss interpolation. Okay? Higher order derivatives. Now, for higher order derivatives, like what I've showed you earlier, okay, like what I've showed you earlier, Taylor series can be used to obtain difference formulas. Okay? Ayan. So, I guess siguro magandang exercise, no? Magandang exercise siguro para sa inyo if you can use the Taylor series so that you can derive all of this. Gaya nung ginawa ko kanina. if you want more guidance, then you can chat me or email me if you have some problems. If ever you did get this by the if you try to get this by the Taylor series. Okay? So in order to shorten all of this, no? In order to shorten all of this, we just say, yeah, i-shorten na lang natin using this one. So F2, F1, F negative 1, F negative 2. What does this mean? So F0, F0 is the point that you want to get. Okay? Fx of 0 is the point that you want to get the derivative from. So an h from, huwag na dyan. I think meron namang figure dito. Tuloy lang natin. And alter. Ayan, yan. Where F1 is f of x plus h, F2 x plus 2h, F3 is x plus 3h. And this is the other notation. So for example, drawing tayo, you have a function like this, okay? And you want to get the derivative here, then this is F0, okay? This is x plus h. This is F1. X minus h. This is F negative 1. And so on. Okay? Ganun lang siya. Just to shorten the equation. Okay. So, yan. We use the formula. What is this? This is the central difference formula, right? For second derivative. Okay. Here. So as you can see, again, if you just substitute the things in the formula, then you can approximate the second derivative of cosine x. So the error is this. Again, take note, x is in radians para hindi kayo malito. Okay? Ayan. Tapos na agad tayo with numerical differentiation. Any questions? So just a summary lang, ginawa lang natin, we use the Taylor series just to derive difference equations. We have defined forward, backward, and central difference. And we have defined how to get higher order derivatives using central difference method, which is derived from the Taylor series too. Any questions? So siguro magandang 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 gawin natin ngayon is to look at your MX and for you to really start programming. So we use our remaining time. So hanggang 1 pa naman tayo. You can have your lunch. But what do you want? Do you want me to group you into groups, tapos may breakout rooms tayo, and what you will do in the breakout room is to probably formulate your flowcharts. Magandang activity yun, no? So that you can start in the MX. Okay ba yan sa inyo? So maybe since 11 participants lang tayo, I can group you into two groups. 11 participants. You're only 9. Or I can group you into three groups probably. Okay. And then I'll share to you a slide. Okay. I'll share to you a Google slide wherein I'll share to you a slide wherein you can edit your flowcharts. Then may umalis. Okay, it's okay. This will help you in making flowcharts by themes. Okay, so how do you want to be grouped? Can do a breakout. Do you want to choose your own groups, or I'll just assign automatically? Okay. I'll just assign automatically. And so I'll just share team slides. Share. Okay. Please go to this link. Sa yung chat. Chat. Ay, sa kanya ko lang na-send. Yan. Please go to that link. Okay. So para may konting activity naman tayo. Okay? And then I'll open the rooms. So you can so please join the rooms.
Sir, pwede pa add ulit sa room.
Ah, wait lang. Close ko muna
Nag-edit
yung
po
mga. Wait, sorry. Ayan, so nandito na kayong lahat. Wait, before we go to the rooms, okay? Before we go to the breakout rooms, here's what you're going to do. Okay. Uh, naka nakapunta na ba kayo doon sa ayan. So naka-access na kayo, no? So may group A, group B, group C. Ayan, pa-send ulit. So here is the link. Ay, mali. Sinend ko. Ayan. So that's the link. What you're going to do is see. Wait lang ah. Yeah. Can you access this? Ayan. So what you're going to do is discuss the machine exercise. And I think ang output nyo after this lab session is have a flow chart. Okay? Have a flow chart that you can use so that guided na kayo sa paggawa ng machine exercise nyo. And of course, I will comment on these flow charts later kapag tapos na kayo. You can also ask me, okay? Ask me. I will go around the rooms so that I can check on what you're doing. Or I can chat doon sa Google Slide and comment. Okay? So, doon sa may mga copies nito, right? You can access this naman, di ba? Itong machine exercise. Ayan. So, please have those. Okay? And you can share. I think I can control who shared. Sige. Now I will assign you to breakout rooms.